Okay, we'll begin. Happy Monday, everybody. It's sixth week, and you guys have a quiz this week. So let me just we'll let me just talk a little bit about quiz 3. Okay, maybe we could do a couple practice problems, and then we'll get after we get that out of the way, we'll take a look at chapter 7. All right, so quiz 3, it's going to cover chapter 6 only. And that means you are responsible for the normal distribution and the binomial distribution. There is a type of problem that I believe appears in your homework, but I don't know if we did any examples in class, so maybe we'll do an example right here. Okay, and so I could say something like, we'll say blood pressure. We'll say the diastolic blood pressure. And I'm making up numbers here, so don't quote me on this. Okay, so we'll say diastolic blood pressure follows a normal distribution. With mean, we'll say 74, and standard deviation 12. Okay, again, I'm just making up numbers. And so I can ask, what proportion of people have blood pressures and we'll say between, I don't know, I'm just making something up here. We'll say between 70 and 90. Okay, so we'll say what proportion of people have blood pressures between 70 and 90. Okay, and the way we go about solving such a problem is we draw a picture kind of like this. So I'll draw my hill here, and so we are centered at 74. I'm going to draw a line over here at 70 and a line over here at 90. And the way I will go about solving this is I'm going to say shade and everything over there, and what I say is total, all the area to the left of 90 minus area to the left of 70 equals the area between 70 and 90. So we find the total area to the left of 90. We subtract off the area to the left of 70, and what we'll be left with is the area between 70 and 90. Okay, and so once we have this set up, then it's not so bad. So we would do z is equal to 90 minus the mean of 74 divided by the standard deviation of 12. I get a z-score of 1.33. I look this up in my table, I find the area to the left of 1.33 is 0.9082. We do the same thing for 70. We'd say z is equal to 70. Subtract off the mean of 74. Divide by 12. We get with negative 0.33. And we look this up in the z table and we say, okay, the area to the left of negative 0.33 is 0.3707. Okay, and therefore the area between is going to be 0.9082 minus 0.3707. And that will give me the area between 0.98 or 9082 minus 0.3707, 0.5375. And there's our answer here. Okay. Are there any questions before we go on? I've put a little practice, quiz 3 practice. This is posted online, so you can take a look. Some practice problems along with their answers. I should give you an idea of what kind of questions you'll see. It's just normal model questions and binomial questions there. Okay. All right, let's do one more kind of practice problem. This time with the binomial. Let's just see here. Okay, so let's say. All right, so the NBA playoffs are going on right now, and we'll see. Okay, so there's a basketball player, Steph Curry. He's very good. Probably one of the best, if not the best, shooter in the league. And so Steph Curry, let's say he has we'll say a 91% free throw rate. I don't know what's his free throw shooting percentage right now. Does anyone know? Okay, this is like really good. Okay, so and we'll pretend. Well, let's assume free throws are independent, and that may be a dubious assumption, but let's just assume they are independent, okay? And that allows us to use the binomial. Okay, so let's assume free throws are independent, and let's say in a game, I'll say Steph Curry will take 9 free throws. Okay, and the question is, what is the probability he makes, we'll say 8 free throws. And then the second one will be, what is the probability makes at least 8 free throws? We'll just I don't know. Maybe we'll make a clicker question out of the second problem here. Okay. So work on. You're gonna have to do the first one in order to get the second one anyway. So work on both of these questions, and let me put up some answer choices for the second one for clicker points here. But I gotta figure out some good answer choices. I think I wrote my numbers correctly, but you can work on this. So these answer choices correspond to the second problem, but you'll want to work on the first one in order to get the second one. Okay, so you'll need, but the answer choices correspond to the second question. What is the probability he makes at least 8 free throws? I'll pause the video here. I'll close the poll here. Let's see. Okay, the correct answer is C, and let's go over this. Okay, so first we'll do the first question. What is the probability he makes 8 free throws? So whenever you have a binomial problem, you got to figure out your n, your p, and your x. And in this case, he's going to attempt 9 free throws. His probability is 0.91 of making a free throw, and the x that we are interested in is 8. Okay, and so in this case, we're going to do 9 choose 8 times the probability of a success, 0.91, raised to the number of successes. So in this case, that has to happen 8 times, and we're going to multiply that by the probability of a failure, or in this case, a miss, and that has to happen 1 time. Okay, so 9 choose 8 is 9, and when I multiply all of this together, you can probably just punch this all into the calculator in one go here. I get 0.3809. Okay, so this is the probability of making 8 out of 9 free throws where order doesn't matter. Okay, and the next question, what's the probability he makes at least 8 free throws? So in this situation, we still have n is 9 and p is 0.91, but this time my x is equal to 8 or 9. Okay, what's the probability he makes at least 8 free throws? That's 8 or 9 for x, And so what we're going to have is we're going to have probability of x equal to 8 plus the probability that x equals 9. The x equals 8 part, we figured this out in the previous step. This is 0.3809. And now we have to add the probability that he makes all 9 free throws. So that's going to be 9 choose 9. This time I'll write it this way. 9 choose 9 times 0.91 raised to the 9 times 0.09 raised to the 0. Now this just reduces to 0.91 to the 9. And when I do this, I get 0.3809 plus 0.4279. All right, so what this means is it's actually more likely for him to make all 9 shots than it is for him to miss 1 shot. So, and then so we add these together, and we get 0.8088. Do you think it's going to be Warriors Cavs again? Maybe. Let's see. Okay, so there you go. That's normal and binomial problems. Okay, so we're about halfway through our lecture time. We'll start the new topic, Chapter 7, and this is on the topic of sampling distributions. Okay, sampling distribution. What is a sampling distribution? This is, technically, it is the distribution of a sample statistic. Okay, so what is a sample statistic? So sample statistics are things like the sample mean or the sample proportion. Okay, and this is in contrast to a population parameter, which is what? So let's just see if we recall these things. So we have sample statistics, and we have population parameters. So the sample statistic is you take a sample and you are summarizing the sample with a single number, right? Okay, so examples are things like sample mean, x bar, and the sample proportion. Which is called p hat. It's the proportion of the sample. Okay. Population parameters, on the other hand, these are properties of the population. So the population has some characteristic, and so this might be the mean of the population or the population mean. What's the symbol we use for the population mean? Mu. And we have the population proportion. Which is P. All right, and we are talking about the distribution of a sample statistic. Okay, so let me try to give you an example or an idea of how this kind of works. I'm going to flip to the next slide. All right, so imagine I have, I don't know, I buy a big tub and I decide to fill it up with M&Ms. Okay, so we just fill, the tub with M&Ms. Okay, fill a big tub with M&M candies. I don't know why I would do this, but let's say I did. And this, we will say the tub is our population. And let's say we went through and we counted every single piece of candy in this tub. Okay, so let's say, so we count every single piece of candy. And I have, let's say, we count 15,600 candy pieces. And for simplicity, we will say we also count 2,652 red pieces. Okay, and so a property of the population is that the tub, the proportion of red candies in the tub is 2,652 divided by 15600. And that's exactly 17%. Okay, so the tub has proportion, and we would use P because this is the population. P is equal to 0.17 red. Okay, so this is the proportion that exists in the population. So the population proportion is P equal to 0.17. All right. This establishes our population. Let's talk about the sampling distribution. So let's say we stir up the tub of candies, and I have like a little scoop, and this scoop will measure out exactly 50 pieces of candy. Okay, so I've got a little scoop here. Okay, the scoop gets exactly 50 pieces of candy. Let's actually make that a little bit bigger. We'll say it gets exactly 70 pieces of candy. Okay, so that's what we have. Okay, so I scoop 70 pieces of candy, and then I'm going to count how many pieces are red versus not red. Okay, we count. How many are red? All right. So we'll call this my first scoop. First scoop, 70 candies. How many do you think are red? All right, let's say 12 are red, okay? All right, so therefore my p hat, my sample proportion is 12 divided by 70. This is not a nice number, but it's what we get. 0.1714. Okay, so that's one p hat that I get. Okay, let's do scoop 2. Scoop 2, I will do another 70 candies. Do you think I'll get 12 red again, or could I get something different? I mean, it's possible to get 12 red again, sure. But maybe I get 10 that are red, okay? So let's say we get 10 red candies. So now my p hat is 10 over 70, 0.1429. Okay, we put this back. And we repeat this, okay? We repeatedly take scoops, take different random scoops of candy. Okay. And every time I do this, I keep track of the different p hats I observe. And the question is, which p hats will occur most often, and kind of what are the different p hats what are the different p hats that I will see, and you know, are certain p hats going to appear more often, certain p hats going to appear less often? That's what we want to know, okay? And so the distribution of all of those different p hats that we are keeping track of, that is our sampling distribution, okay? So we repeatedly take different scoops of candy. We'll say we do this 1,000 times, 10,000 times or something, okay? We keep track of all the p hats, and you know, what is the distribution of the p hats? Okay, and that question, what is the distribution of the p hats? That is our sampling distribution. All right. Can we kind of conceptualize what's going on here? There's a computer app or a website that does this. Let me find this here. It's actually the app uses Reese's Pieces candies rather than M&Ms, but it's the same idea here. Let me zoom in here. Okay, so Reese's Pieces, I don't know if you guys know, it's like the same thing as M&Ms, except they got peanut butter inside, and there's only 3 colors. They're like orange, yellow, and brown. And so let's say we're going to specify 30% of our candies are orange, and we're going to take scoops of 50. And we're going to keep track of the different proportions that we'll see. So I'm going to just do one, and what this is going to do is mixing up, this is like our big tub of, Reese's Pieces candies. If it's orange, it's going to put over here, and then if it's yellow or brown, it's going to put over here. So I'll just animate the first one. There we go. It's going to keep drawing until it gets a total of 50 pieces of candy, and it counts out 20 pieces are orange, 20 pieces out of 50. So we do 20 divided by 50, it gets a p hat of 40%. Okay? And then it plots the 40% right here, kind of and it's going to build up a dot plot here. And this is how we'll keep track of all the different p hats that we see. I'll do another one of these. Okay, so it's mixing out the candies, puts the orange ones over here. So this time, when we scooped out 50 pieces of candy, we got 12 orange pieces. 12 out of 50 is 24%. So it puts a dot right here for 24%. So here we get 15, 16 orange pieces. 16 out of 50 is 32%. It puts a dot right there at 32%. Okay. And here's another case. This time it got 32% again, and it puts a dot there. Another instance of 32%, let's just see. This time it only got 11, so 22%. And so we can just keep repeating this. We get 34% this time, 22% that time, 38%, 28%, okay? And so after drawing 10 samples, these are the proportions that we've observed after those 10 samples. Now I can kind of speed things up and I can say, well, instead of doing one at a time, just do 10 at a time. Okay, so this is after 20, here's after 30, and after 50 samples, we're starting to get some kind of shape here. And let me just kind of speed things up. So we'll do 100 at a time. Okay, and so after 250 samples, we start to see that, okay, 30%, 32%, 28%, those appear quite frequently because what we've specified that in the entire population, 30% are orange. Okay, so we've specified that 30% are orange, so it makes sense that when we draw random samples, we're getting something, most of the time we're getting something close to 30%. But because it's random, we can get higher than 30%, we can get lower than 30%. So because of the random nature, sometimes we've seen as low as 12 or as high as 50%. And so we keep drawing, and I'm going to just keep cranking this up. Here's 1,000 at a time. And we can see that, so what happens is the dots will start to get so close together that they just merge into lines. But the relative heights still give us an idea. Okay, so this is after 1,300 samples. We start to see, kind of a unimodal and symmetric shape here. So this is about after 7,000, what does this shape kind of look like? It looks kind of normal, right? Like I can put a normal overlay, a normal curve over it, and we see that this distribution looks a lot like the normal distribution. Okay, this is the sampling distribution of all the different p hats that I've observed. All right, so again, the idea is we've specified in the population which is going to be our tub of candies, we've specified a certain proportion, and then if we repeatedly draw samples from that population and we keep track of all the different p hats, then we can generate our sampling distribution. So let me put this on the next slide here. Here, actually, I'll screenshot this thing. And so the idea is we specify that the population is exactly 0.3 orange. Okay? So when we draw random samples, we expect, most samples to have a p-hat close to 0.3. But of course, because of random chance, it will not be exactly 0.3 all the time. And so in this situation, our most recent draw a 12 orange out of 50 pieces. So p hat is equal to 0.24. Okay? And we add a dot to this column. Okay. And so the resulting dot plot is the distribution of all the p hats that we have seen. So this is kind of the introductory concepts to a sampling distribution. And if we can understand the nature of this sampling distribution, we can start answering questions about the samples that we see. So I can say, what is the probability that I would get a random sample where I get 40% of my candy pieces are orange? Okay, and we can start to answer those questions. I think we're going to run out of time, so we'll just call it a day here, and we'll end here, and then we'll pick up on this topic on Wednesday.